Okay, so calculating standard slopes in multiple regression is very simple, thankfully. And SPSS, of course, will do this for us. But it's nice to kind of look at what contributes to a small versus large beta weight. So first of all, what is a beta weight in multiple regression? Well, it indicates the expected change in the DV that would be associated with a 1 standard deviation increase in the predictor, because remember, beta is standardized. And it does this while controlling for the presence of the other predictor. So basically, a beta is a standardized slope, just like it in multiple regression here, just as it is in simple regression. So what you can do is just run the bivariate correlations between, or I'm sorry, among these variables. So we have salary as our DV, we have number of pubs, and we have year since PhD. So go ahead and open the data set and run these correlations, and hopefully they'll turn out just like the ones here on this slide. And we're going to designate year since PhD as predictor 1 and the other one as predictor 2. So here are the formulas. RY1 for the first beta Y 1.2, that just indicates the beta for the beta weight for predictor 1 while controlling for predictor 2. That's all that means, that 0.2 part. And so we have on the numerator, first we have RY1, which is the correlation between the DV and predictor 1. So that would be salary and year since PhD, and that looks like a 0.608. And then we have minus and then a product term. We have RY2, which is the correlation between salary and predictor 2, which is 0.506. And then we have an R12, which is a correlation between the two predictors. And this is also called a multicollinearity term, and that's just a fancy term for the correlation between two predictors. And so that is, let's see, the number of pubs and year since PhD, that is 0.651. We knew that from the last slide, actually. So you would calculate that, and then on the denominator you have 1 minus, and then you would square the 5.06, I'm sorry, the 0.651. That's the multicollinearity term with the two predictors, the association between those two. So when you calculate all that out, the answers are in the bottom of the slide in the notes. You can check your answers, and you can do the same for the beta 2, and that's the slope for the predictor number of pubs in predicting salary there. So you can look at both and get those beta weights, and then after you've done that, I want you to just look at this formula and just become comfortable with it. Don't let it scare you. It's not scary at all. And just look in your mind's eye what will happen when we increase the multicollinearity number. So that's the R12. That's the correlation between the two predictors. And to the extent that that gets larger and larger, we will see that the unique variance accounted for by each of the variables decreases. Okay, so more on this later, but as the R12 increases, the multicollinearity or the association between the two predictors, we expect the beta to fall. Now the beta is the slope, the standardized slope, but it is also an index of the unique variance accounted for by that predictor. So accounting for the other variable in the model, what is the unique variance contributed to salary by each of these predictors? And to the extent that they're correlated with one another, they're not going to explain unique variance with the DV. So if you go back to the Venn diagram, and again in your mind's eye, increase that C space by bringing the two IVs together. And look what happens to the A and B spaces. They decrease. So just keep thinking about that. Let it sink in. The higher the correlation between the two predictors, the less likely that either one will uniquely contribute to the DV. That's just the way it is. It's not a bad thing necessarily or a good thing. but it's a good, it's kind of a nice thing to know, just so that if you have two predictors that are very highly correlated, you can probably discard one because they're redundant with one another and they're not predicting uniquely, adding anything to the model. So at the extreme case where the predictors are coming closer and closer together and they're almost fully overlapping such that that C space is huge, it's probably best to drop one from your model. So that's kind of the practical implication of what's going on with multicollinearity.